Today we are very happy to have Professor Zhang from Stanford University who gives today's colloquium. Cheng got his degree in 1987 from Stony Brook, and then he went for postdocs at Santa Barbara. He spent several years at IBM before he joined the faculty at Stanford. And some of you might remember that he gave a colloquium a few years ago on the quantum spin Hall effect. Now, it's a little bit unusual to have the same speaker coming back to give yet another colloquium after only a couple of years. And the reason for that is that this is a field that has absolutely exploded in recent years. The general field of topological state, topological insulators, topological superconductors. And Professor Zhang is not only a key player, but is also one of the very originators of these fields. So we are very happy to have him here to tell us the latest in this exciting field. Please.
Yeah, thank you very much, Hans. So today I'd like to tell you about maybe the more recent development of topological insulators and superconductors. So let me first acknowledge my collaborators. First, extensive collaboration with my own theory group at Stanford. Many young people have since moved on to take faculty positions. And extensive collaboration with colleagues at Stanford University, experimental colleagues. And some of the earliest experiments were done at the University of Würzburg in Lawrence Molenkamp's group, and also more recently extensive collaboration with colleagues from China. So today the plan will be talking about models and materials of topological insulators, and then I'd like to tell you about topological field theory and what's the general theory of interacting topological insulators. And then I'd like to tell you about something that is still a theoretical prediction, but we are trying to find experimental realization of quantized anomalous Hall effect, which is quantum Hall effect without external magnetic fields. And then we talk, maybe if time permits, we talk about topological superconductors and Majorana fermions. So basically in condensed matter physics, we're looking for new states of matter. So that search is somewhat different from chemistry, for example, where they searched for fundamental elements almost 100 years ago, and that was the golden age of chemistry, or the search for particles in the case of particle physics, accelerator physics, maybe the high point was 50 years ago. But in condensed matter physics, we try to look for how basic elementary building blocks are put together to form new states of matter. Such as a crystal, a magnet, and a superconductor, and so on and so forth. So most of these states in condensed matter, they are simply described by a very simple principle called the principle of spontaneously broken symmetry. We say that a crystal is a unique form of matter that breaks translational symmetry spontaneously, and a magnet spontaneously breaks the rotation symmetry, and the superconductor breaks some gauge symmetry, which is a little bit more subtle, and actually the precise understanding of which led to the fundamental mechanisms in the standard models, such as the Higgs mechanism. So this is the situation of condensed matter physics maybe before 1980, where most of the states are these states described by an order parameter and by a broken symmetry. But then in 1980, Klaus von Klitzing discovered the quantum Hall effect, and which is now realized as kind of the first topological state of matter, that so when you look at it, the whole conductance is precisely quantized to be some integer value, and that integer value in units of E squared over H can be cast as a topological invariant measured in momentum space. So Hans Hansen was a professor when I was a student at Stony Brook, and we collaborated extensively, and one thing we proposed is that the quantum Hall effect is described by a topological field theory, which is described by a Chern-Simons term. So that's different from the ordinary field theories such as Maxwell theory or Einstein theory, which are geometrical, and these are kind of topological terms, and for topological reasons, these coefficients are precisely quantized, and it describes the long wavelengths and low energy physics of these quantum Hall effects. But the condensed matter physics at that point looked like in a very strange situation. that almost 99% of the states are these spontaneously broken symmetry states, and there's only one topological state of matter in the quantum Hall effect. So ever since then, physicists have been looking for new topological states of matter, and very recently it becomes very active. And the discovery was first made in the 2D topological insulator. At that time, it's also called the quantum spin Hall effect, and that was a theoretical prediction made by our group that Mercury telluride material is a two-dimensional topological insulator material when the thickness was chosen appropriately. And very soon, there was an experimental confirmation of that. And later, now there are developments in three-dimensional materials, such as bismuth antimony and bismuth telluride and bismuth selenite. So this is now the key focus of more recent experimental efforts on bismuth telluride and bismuth selenite. These are materials which are in the bulk have a full gap, but on the surface it has a surface state which is a simple Dirac cone located at the gamma point. So this is one of these strange things in condensed matter physics that maybe 5 years ago you never heard about this concept of topological insulator. And these days when you look, it's almost everywhere. In particular, it went into the popular culture. How many of you have watched Big Bang Theory before? So I don't know whether you have seen these episodes.
Good evening. I'm your guest lecturer, Dr. Shou.
Mercury telluride topological insulator.
I was expecting applause, but I suppose stunned silence is equally appropriate. I agreed to speak to you this evening because I was told that you're the best and the brightest of this university's doctoral candidates. Of course, that's like saying you're the most important electron in a hydrogen atom. Because you see, there's only one electron in a hydrogen atom. Best and brightest, my sweet patootie. All right. Let's begin. Show of hands. Who here is familiar with the concept of topological insulators? Don't kid yourselves.
I found another tweet from a student at Cheng's.
So this is a subject which is now extremely popular now in condensed matter physics. And today I hope to give you a very basic introduction to the subject, and hopefully you will have time to come to some frontier topics. So this is kind of the fundamental physics motivation. But at the same time, condensed matter physics is also driven by some possible practical applications, such as the understanding of the quantum theory of solids led to the concept of semiconductors, and so on. But today, actually, there's a tremendous problem in microchips that the overheating of the microchips is basically causing some fundamental problem that it's preventing the scaling of Moore's law. And fundamentally, it is because of the fact that electrons are strongly interacting, and in the solid, when you try to push the electrons through, it's like moving cars in a crowded marketplace, and they keep have collisions with each other and with the impurities in the system. So what we like to do is that inside the chip, we achieve a principle like the highway principle. And you see the basic principle of why the cars can move so smoothly in a highway. The fundamental idea is that the spatial separation of counter-moving traffic, so that on the right side, you only have forward-moving traffic, and on the left side, you only have the backward-moving traffic. So this may appear like kind of a cartoon picture, but this, as we will see, is perhaps the best illustration of the ideas of topological insulator, that things are only moving at the edge, and the counter-moving traffic are spatially separated. And the first realization of that is in the quantum Hall effect, where if you think about if you have a one-dimensional system, and for the moment, if you neglect the spin degree of freedom of the electron, you will have possibility of forward-moving and backward-moving modes. But if you have some impurity, you will, of course, lead to scattering for forward-moving mode to backward-moving mode. So now, if you have the quantum Hall effect, it achieves this spatial separation of these two counter-propagating modes, so that on the upper edge you have only the forward moving mode, and on the lower edge you have the backward moving mode. So you achieve this spatial separation by embedding this one-dimensional channel into one higher dimension, which is 2 dimension. So then you can have only the forward moving traffic on the upper edge. So in this case, if you hit some impurity, the electron will simply take a detour and keep on moving forward. And because the probability to backscatter would imply that you have to cross all the way to the other side of the sample, which has exponentially suppressed probability. So the idea is to generalize this picture to include the spin degree of freedom of the electron. And so if you look at the spin degree of freedom, then even in one dimension you have 4 fundamental modes. You can be spin up or spin down. You can be forward or backwards moving. So the idea to generalize the quantum Hall effect to quantum spin Hall effect, which is now also called the 2-dimensional topological insulator, is to get a spatial separation into 2 and 2. But here, these two actually form a time reversal invariant pair. You have spin up forward and spin down backwards, and that actually preserves time reversal symmetry, whereas in this case, the time reversal symmetry is actually broken explicitly by the external magnetic field. So this is, when you look at this picture, actually what is microscopically responsible is basically you have to have the electron to have a sense of rotation, and that is dictated by the external magnetic field, and that's by the right-handed rule tell you that the electrons have a preference to going around the sample in a clockwise fashion. So here the idea is like replacing the external magnetic field by the spin degree of freedom, and because you have 2 spin, you have spin up and spin down. Spin up is moving around in a clockwise fashion, spin down is moving around in a counterclockwise fashion. It's like having 2 copies of quantum Hall effect. But you will see that the fundamental interest is that this decomposition is actually protected by the time reversal symmetry. But just looking at this picture, you see that the fundamental microscopic force important here is that it requires kind of a spin-orbit coupling, because the orbital motion and the spin motion are intrinsically coupled to each other. And there were some earlier proposals to realize this kind of situation in graphene and strained gallium arsenide, and none of them worked because the spin-orbit coupling is not strong enough. And I will, of course, tell you what worked in the end. But you will first see what is kind of the principle which protects this edge state from backscattering. Here is quite obvious because there's no backward moving modes. Here you both have forward and backward moving, but there's a perfect correlation that upspin is going forward and downspin is going backward. So now what happens if you have this situation and the electrons are moving at the edge but hit a non-magnetic impurity which preserves time reversal symmetry? Then because the electrons are waves, they can actually, in principle, backscatter, but you have to add up all the possible amplitudes for possible backscattering. So if you have forward-moving electron, and if they hit the impurity, they are moving back, let's say going around the impurity in a clockwise fashion, then the spin also have to rotate adiabatically in a clockwise fashion from up to down. So in this case, it rotates by pi. But for every path like that, there's also the possibility to do the time reverse path, namely the electrons going around, but moving around the impurity in a counterclockwise fashion. And in this case, the spin also moved around, turned around in a counterclockwise fashion. In this case, then rotates by minus pi because it's counterclockwise. So now we have to add up these 2 possible backscattering paths in the sense of quantum mechanics. But then we need to look at the phase difference between these 2 processes. But now we look at, in this case, the electron rotates by pi, and the electron spin here rotates by minus pi. So the net difference is pi minus minus pi, which is equals to 2 pi. And now we remember another fundamental property of the electron, namely when it's spin 1/2, and when you rotate it by 2 pi, it gives you a minus sign. So that tells you, this minus sign tells you, or this notorious fermion minus sign tells you, that these 2 amplitudes always add up in a destructive interference situation, so that they always cancel each other exactly. So then there's no possibility of backscattering when the electron is moving around the edge, even though you have both of these traffics present. So this is kind of the reason, when you look at semi-classically, why this state is a stable situation. And another way to look at it is in the momentum of wave vector space. So we know that ordinary insulators have the situation that they have a conduction band and the valence band, and no states here in between. So, but there are also insulators or semiconductors which have mid-gap states, states which live inside the gap and spatially localized on the surface of the material. So in this case, you think these two situations look rather different, but if you add some perturbation which preserves time reversal symmetry, you see that these degeneracies can actually be lifted. And if they can be lifted a little bit, you can lift them even more. So then in this sense, we say that there's no topological difference between this set of states and this set of states. You can actually exactly map them one to each other, and these are all the valence states, and these are all the conduction states. What is fundamentally different in the case of quantum spin Hall effect or two-dimensional topological insulator is that you have a conduction band and the valence band, you have a bulk insulating gap, but on the boundary there are these edge states. You have on one side of the edge upspin dispersing positively and downspin dispersing negatively, and they cross at one point, which is a time reversal invariant point. So now at this point, there's a fundamental theorem in quantum mechanics, which is the Cramer's theorem, which tells you that at this point, all states have to form AA degenerate pairs, according to the Cramer's theorem of time reversal invariant system. So now if you change your Hamiltonian slightly, but still maintaining always the time reversal symmetry, then the only thing you can do is to shift that degeneracy point up or down. But you cannot remove that degeneracy to get into a situation like that, because that will violate Cramer's theorem. So that tells you that in this case, you have tied a knot between the conduction band and the valence band, and the knot cannot be untied unless you break time reversal symmetry. So in that sense, the situation we're dealing with is like this is a topologically non-trivial state, and this is a topologically trivial state. And the fundamental importance here is the time reversal symmetry, which preserve this Cramer's degeneracy point, or this knot, cannot be removed. And in that sense, it's fundamentally different from the quantum Hall effect, which breaks time reversal symmetry. So now the question is, where in nature can you find such interesting topological state of matter? So this is a chart which is often used by semiconductor physicists, plotted in the space of energy gap and lattice constant. For example, energy gap can be easily turned into a color plot, converting the energy gap into a wavelength or a color. And so the lattice constant is also very useful for semiconductor physicists to build heterojunctions to put one thing on top of each other. So the first proposal for a topological insulator material, when we encountered this situation of many semiconductor material, it was one thing that hinted to us is that in this energy diagram, not only the energy gap can be positive, but some material can also have a negative energy gap. So the absolute zero of the energy is here, and most of the material, as you would expect, have a positive energy gap, but there's one material called Mercury telluride, which has a negative energy gap. And the thing that caught us attention was because when I was a student at the Stony Brook, when Hans was a professor, I learned a little bit about topological quantum field theory, and in particular there was a result that 2 + 1 dimensional Dirac equation will induce a Chern-Simons term whose coefficient, the sign of the coefficient, depends on whether the Dirac mass is positive or negative. And it was this kind of hint which helped us to realize maybe this negative gap material is the one that is topologically non-trivial. And throughout the work, we also discussed extensively with colleagues in the University of Würzburg. So most semiconductor material, the band diagrams, energy level diagrams, can be easily understood when you look at the simple atomic level picture. So you have the S level and you have the P level. And they also have a spin-orbit coupling. So S level has L equals to 0, so it does not split under spin-orbit coupling. But the P level has L equals to 1, and under spin-orbit coupling, it splits into P3½ and P1½ levels. So this is the energy level splitting, which is caused by spin-orbit coupling. So now going to from the atomic energy levels to the solid-state bands, you basically merge these atomic levels into a band. So the S levels merge into this conduction band, and the P levels merge into the valence band. And that's the situation for most semiconductor material, such as gallium arsenide and cadmium telluride. But by the time you go to heavier and heavier elements, such as mercury telluride, some dramatic things happen. First of all, because of the heaviness, the spin-orbit coupling becomes stronger, so the splitting of the p level is much larger than what is in the lighter elements. At the same time, there's something called a Darwin term, which pulls the s level down. But the combined effect of both of these in mercury telluride is that it causes the p3 half level to lie above the s level. And so this p level now becomes effectively the conduction band, and the gamma 6 or the s orbitals becomes now the valence band. So semiconductor physicists make a definition of the sign of the gap to be s minus p. So in mercury telluride, it's the other way around, and that's why it has a negative energy gap. So now, when we get into this situation of mercury telluride, but then there's also the material cadmium telluride, which is a positive energy gap, and the combination of them enables some very interesting construction of quantum well structures. So you now put mercury telluride between the cadmium telluride, and now you can consider two possible limits. In one limit, which is the thin limit, and the other is the thick limit. In the thin limit, you will expect the mercury telluride band structure to be less relevant, so the cadmium telluride band structure will be more dominant, and that has the feature of s level above p level. But now, by the time you get to mercury telluride, which is thicker, then the other situation you have to realize, namely the p level has to lie above the s level. So when you tune this thickness of the mercury telluride quantum well thickness, somewhere a quantum phase transition has to occur. And that happens around 6 nanometer in the thickness of the quantum well. So now the reason why this is important is that because the effective description of the mercury telluride two-dimensional quantum well is a Dirac-like model, effective model. And I'd like to explain to you very briefly how this comes about. So you have basically this s orbital, you can be spin up, spin down, and you have this p orbital for which you take the strongest spin orbit coupled levels, which are called heavy core levels. And basically for spin up, you like to take Lz equals to 1, and for spin down, you like to take Lz equals to minus 1. And you try to write down a tie binding model for these 4 levels. And you block diagonalizes because the coupling between up and down to the lowest order is not that relevant. So now when you look at the diagonal in one of the blocks for spin up electron, you have the energy level difference in the diagonal element. That's the energy level difference between S and P. But on the off diagonal element, you have the coupling between the S level and the P level. So now because they have the opposite parity, so they have to couple only at some finite momentum, in particular at k equals to 0, they cannot couple because they have the opposite parity. And that's why when you go to the low energy long wavelength limits, k close to equals to 0, they actually give you linear matrix element in k. And in the diagonal element, it starts out with a constant. And that's kind of how a Dirac-like structure emerges in the low energy sector of a condensed matter system, because the off-diagonal coupling has to be linear in k, and so the diagonal element tells you the mass difference. So the energy level difference between S and P orbital give you the mass of the effective Dirac equation, and the off-diagonal term give you the effective velocity of the Dirac equation. So now by now in condensed matter physics, we don't find it so surprising to find Dirac equation anymore in condensed matter physics, because graphene is a very well-known example where similar situation occurs. But now we have a situation where you have this massive Dirac equation in 2 + 1 dimension, but with a wonderful opportunity to tune the sign of the mass. And so it can be turned from positive to negative as you change the thickness. So basically, when the mass becomes negative, when you try to solve the Dirac equation, as if outside it's like the mass is positive and inside the mass is negative. So it looks like a mass domain wall for the Dirac equation, and the domain wall position is exactly at the sample boundary. So anyone who has solved this kind of Dirac equation will know that it will always attract some bound state or solid tonic-like solution at the place where the mass changes sign. So that's why there are always two bound states, one for spin up, one for spin down, but for a given momentum, let's say kx equals to 0. So these are the two bound states. But when you change kx, you will find that these bound states will shift in their energy in the opposite direction, and that's how it sweeps out a dispersion relation with the opposite group velocity. And so this is kind of the fundamental reason. A, mercury telluride is a material which is described by a 2 + 1 dimensional relativistic Dirac equation, but B, the mass of the Dirac equation is continuously tunable, and even the sign. And there's a critical phase transition that happens when the thickness of the mercury telluride field is about 6 nanometers thick. And below that, mass is positive, you don't get these solutions, but above that, you get this negative band mass, and it leads to these solitonic solutions at the boundary. So this is the realization we had in 2006, and we immediately got very, very excited. So we find an example of this non-trivial topological material in nature, and the question is whether it can be tested experimentally. It turns out that there's a very well-known group in Europe, in Germany, Würzburg, and they are the experts in making mercury telluride quantum well structures. They have been working on it for 20 years. And in this system, you'll find that the mercury telluride thickness can be tuned by the NB growth. And by putting a gate electrode on this system, you can actually change the Fermi level of the quantum well, and thereby going from conduction band to valence band, and so on. So for us, the most important tuning parameter is one is the thickness, and the other is the gate voltage. So now, what do you predict? You predict that in the thin limit, you have a conduction band, you have a valence band, and you have no states in between, because this is a trivial insulator in our modern language. So in this case, when you tune the Fermi level from the conduction band to the valence band, in the middle, in the band gap region, you find no states, and you find infinite resistance. But in this case, when the quantum well is thicker, you will, so in between, you went through a topological phase transition, and in this limit, you will have conduction band, valence band, but you have a pair of edge state which go across from conduction band to valence band with this Dirac point here in the middle. So then when you tune the Fermi level from conduction band to the valence band, then you will go through a region in the region where there's a bulk gap, but there are still conducting edge states. So it can carry a current and can give you a conductance. And because there are two axis edges, two channels, if you increase the voltage here, you have more current here in the red channel and more blue current here in the spin down channel. And these two channels will give you a conductance of 2 E²/h. And that was experimentally tested. They grow a system of different layer thickness, and you find that indeed it's an insulator with no conductance. But in this case, it is an bulk insulator that has edge state conduction of 2 E²/h. And the important thing is that the difference between edge state conduction and bulk conduction is very well defined. As you change the cross-section of the sample in ohmic conduction due to bulk conduction, you will actually, if you make the cross-section larger, you will have higher conductance and lower resistance. But if the conduction is due to the edge state, actually it should not change, because there are always these two edges. And that is exactly which was observed experimentally. And a lot more striking experiment has been done more recently in the so-called non-local transport in the quantum spin regime. And that when you make a device of the shape of English letter H, and you try to pass a current from 1 to 4, but you try to measure voltage between 2 and 3. And in ordinary ohmic conduction, you will not expect to measure a voltage between 2 to 3. But here, because of the edge state conduction, the current has to go all the way around the sample edge, and therefore it has to induce a voltage between 2 and 3. And that gives rise to this non-local conductance, which the edge state picture can precisely predict what they are quantitatively. And when the experiment was carried out a little bit more recently, they find almost perfect agreement with the theoretical prediction. And this is why Marcus Büttiker, who did a lot of work on edge-state conduction, find that this is really, finally, absolutely convincing proof that we have reached the quantum spin Hall regime with 2D topological insulating regime with purely edge-state conduction. Now, more recently, so far, these are the experiments done in Mercury telluride quantum well, and so more recently, there's another two-dimensional topological insulator material in the indium arsenide gallium antimonide heterojunction structure that was also predicted by our theory group in 2008. And recently, there's a beautiful experiments coming out from University of Rice with Ray Duke's group, which basically sees similar things, but now in a completely new material. And that material also is a lot more accessible to a lot more people. I hear that here in Sweden, there's also a lot of work on this. So now let's move from this two-dimensional topological insulator to three-dimensional topological insulator. But the discovery of Mercury telluride basically pointed us to where to look for in the periodic table. Basically, Mercury is here and tellurium is here, and it tells us that maybe the first place to look after the discovery of Mercury telluride topological material is in the lower right corner of the periodic table. On the lower corner, because the spin-orbit coupling is stronger, and on the right side of the corner, because these are SP systems in which calculations can be a lot more precise. And then we very soon landed on a very important three-dimensional topological insulator material, and that's in the case of bismuth selenide, bismuth 2 selenium 3, or bismuth 2 tellurium 3, which I like to tell you about. So now these are materials which form quintuple layered structure. So the basic unit, so it's a flaky-like material, quasi-two-dimensional material, and it's strongly coupled within this quintuple layer, but between the quintuple layers, it's weakly coupled. So in this case, you have this quintuple unit, and that repeats. So it's a little similar to graphene. Graphene has one layer which keeps on repeating, but here it has 5 layers which keeps on repeating. Now, what is the important electronic structure here responsible for the topological insulating behavior? Let's try to understand it step by step, and I promise you, you only need to understand some very basic quantum mechanics to understand the situation here. So now you have this one unit cell with 5 atoms, 2 bismuths and 3 selenium. And the important orbitals are all p orbitals. And so you find you have bismuth the bonding orbital, p orbital, and anti-bonding orbital, because you have a center of inversion here, so you can form bonding and anti-bonding states with respect to the central inversion layer. So you first form bonding and anti-bonding states. And now you look at these 3 p orbitals, but they are not equivalent because it's a two-dimensional system, so that's why pxy is different from pz. So this is like crystal field splitting. So now near the Fermi level, you find only the pz orbitals relevant near the Fermi level. And now it is the bonding pz orbital of bismuth, but anti-bonding pz orbital of the selenium, which lies closest to the Fermi level. So now, when you turn on spin-orbit coupling, you find there's a level inversion again between these p orbitals. So the basic physics is very, very similar to that of the Mercury telluride system. But how do you tune something like spin-orbit coupling continuously? In the case of Mercury telluride, because it's a 2D material, we're simply changing the thickness of the Mercury telluride layer. Now these are 3-dimensional material, what do we change? Fortunately, nature gives us 4 materials to play with, which all have more or less the same property, and main difference is the strength of spin-orbit coupling is different. So in these 4 material, that's our theoretical work, which shows that this material does not have enough strong spin-orbit coupling, so it's still in this regime without the band inversion. But these 3 material have strong enough spin-orbit coupling, and the bands are inverted. And because of this inversion, it now leads to this behavior. So, so in the topologically trivial regime, you have conduction band, you have a valence band, and you have this surface state which now connects the conduction band and with the valence band. And that gap is also reasonably large. It's about 0.3 electron volts. So the surface bands which connects the conduction band and the valence band, they cross at one point, and that's a Dirac point at a time reversal invariant momentum, k equals to 0. So now the analytical modeling of this system is also very simple and very beautiful. You again have these 4 levels which are closest to the Fermi level. You have the PZ bonding and PZ anti-bonding. You have spin up and spin down. So altogether you have these 4 levels. And so what you have is that basically it becomes a relativistic Dirac equation now in 3 plus 1 dimension. So you again see that because these are states with the opposite parity, the matrix element which couple them have to be linear order in K. That's how a Dirac structure arises. And on a diagonal element, you have the energy level difference between the bonding and anti-bonding states. And so that looks like a mass term for the Dirac equation. And so the important thing is that spin-orbit coupling drives an inversion of the mass. So if the mass is positive, it's trivial, and when the mass is negative, it's non-trivial. So it's exactly the same physics as it happens in the case of Mercury tellurides. But now this is a 3D material, then on the surface, it will have a simple Dirac cone. So it's a 3D bulk system, but the surface state is 2-dimensional, and that's described by a single copy of the Dirac equation. The derivation of it is very similar to, again, what we did in the case of Mercury tellurides. So the important thing is that there's only one state for one given momentum k. And so that's, in that sense, there's only a single Dirac cone on the surface. So in this very precise sense, the surface state of bismuth telluride is 1/4 of that of the graphene. Graphene, where we like it because it's also described by massless Dirac equation, but there are 4 of them. There are 2 Valley degeneracy and 2 spin degeneracy. Here, there's no Valley degeneracy. It's happening at the gamma point, k equals to 0. And it has no spin degeneracy. For a given k vector, there's one unique spin direction. So when you look at it, it looks like the positive energy states of the surface band is a left-handed helix when you follow the spin. And the negative energy states forms a right-handed helix. So that feature is again very similar to the properties of the neutrino that we observe in the world of elementary particles. We know that the neutrino is a left-handed particle, but the anti-neutrino is a right-handed particle. So that feature is exactly mimicked by this structure. So this surface state, in that sense, very precise sense, is a very deep thing, and it mimics some very profound features, what we also observe in the world of elementary particles. So now the community gets really excited because they finally also give you materials which you can test by standard surface probe techniques, such as APRS, angular resolved photoemission, and STM. So now this is the experiments done at the Stanford group, in the Cheng group, and they took bismuth telluride material, and that again has a bulk gap, but when you look at the surface band, it indeed has this beautiful linearly dispersing Dirac cone shape. When you look at it slightly at higher energy, the cone is not forming exactly in a circle, but forming a little bit of a hexagonal warped structure. And that's because the underlying lattice is a hexagonal lattice. And the circular approximation will only get better and better when you approach the Dirac point. This is the experiment done at the Princeton group, where they worked on bismuth selenide, and you see again this Dirac cone feature, but now they also did spin resolved photoemission, and they find that the spin orientation indeed form a left-handed helix for the positive energy bands. Let me also remark about a problem that's persisting in this field, and that's because we say, theoretically, predicting that these are insulating materials in the bulk. But when you actually make the material, somehow due to some chemistry of selenium vacancies, it's actually slightly electron doped in the bulk. So the Fermi level not only intersects this surface band, but also intersects this bulk conduction band. And that's the problem the field is trying to solve. now, not only you can use uppers, you can also use STM experiment, and that is done by my colleague Aaron Kapitunik at Stanford University. And basically, they can test this picture I explained earlier, that electrons going positive momentum, they have to go back with negative momentum, but with the opposite spin. And that backscattering is not allowed by time reversal symmetry. So basically, by looking at the surface electron waves scattered by impurities, they can actually check if this selection rule is satisfied, and indeed it is satisfied. So that's kind of a confirmation of the physics of no backscattering. So now it also kind of challenges the material science in this field. So you have to grow very good material, but hopefully you can also look at this material by powerful probes as you are growing. And at University of Tsinghua in China, before topological insulator became popular, they already developed a system which has both growth capability by NBE, but also STM and uppers measurement in the same vacuum connected system. So it's a very, very powerful system, and indeed some very interesting thing has been seen. So one thing you like to see is that we say that basically you have the one Dirac cone here, and other Dirac cone is on the other side of the surface. And that's how you kind of evade this fermion doubling problem, that the other one is very far apart. But when you bring them close to each other, then there's a hybridization between these two cones, and the gap will open up. So the experiment to do then is to grow the material layer by layer. Actually, you can only do this quintuple layer by quintuple layer. And for every quintuple layer growth, you take an opposite spectrum. And that's what was done in this Tsinghua University experiment. And you indeed see that there's a gap when it's thin enough, and the gap slowly closes when you are beyond 5 quintuple layers. So 5 quintuple layers is roughly the magic number beyond which the massless Dirac cone is already observed. So now the other thing you can do is to look at the quantization of the surface state under a magnetic field. And that, you remember, was the first important experiment in the case of graphene. When they identified a single layer sheet of graphene, they tried to look at the relativistic Dirac model in a field, and that leads to a lambda level quantization which has a unique spacing with square root of b in difference with ordinary non-relativistic system. And that is also what has been observed again by this group at Tsinghua University. When they pop the STM tip on the surface, applying a magnetic field, but then change the voltage, they see these different peaks, and that are indications of lambda levels. And you plot this peak spacing, and you find that it's indeed scale with the square root of b. So now I remarked that this problem that we always have is that in the business selenite class of material, that it looks like the transport still has bulk contributions, and that's a problem material scientists in the field are trying to solve. But we already actually have a system of a clean 3D topological insulator, but again in the Mercury telluride system. So now you go to really a thick Mercury telluride layer, not just a 2D quantum well, but going to a bulk insulator. And actually you can only achieve an insulating behavior in Mercury telluride by applying some pressure or strain. And then it opens up a gap, and we predict that this gap is a non-trivial gap in the sense that there's also a surface state which goes through. So now how do you tell experimentally that you got it? You got a true three-dimensional topological insulation. The idea is to perform a quantum Hall measurement, because then you have this 3D material, and normally you don't expect any quantization behavior. But if you only have 2D electron gas on the surface and the bulk is insulating, then even in this 3D material, you will expect to see what is the 2D quantum Hall. And that's the beautiful experiment that was done, again, very recently in Lawrence Molenkamp's group, which sees that this 2D quantum Hall effect with this precise plateau quantization, and that can only be possible if there's no bulk conduction in the system. So the true 3D topological insulator behavior has been observed in a Mercury telluride system. So now the field is kind of really exploding, and people are trying to find all sorts of materials and compounds. And that's just one example that in collaboration with Claudia Fels's group in Germany, we're predicting that these Heusler compounds are also topological insulators. And the important news is that there are 50 of them, and they all have interesting interplay between conventional orders and topological orders. So that's a field that's also developing very rapidly. So now let me move on to one frontier topics in the field. And we just look at the nomenclature. We have the Hall effect, we have the spin Hall effect, but we also have something called the anomalous Hall effect. And that's basically due to the magnetic moments in the system, which can lead to a Hall effect because it breaks time reversal symmetry. So all these have been observed in these years, these more than 100 years ago, spin Hall effect more recently. But it looks like for every Hall effect, there's a quantum version. So for the Hall effect, there's the quantum Hall effect, very important, both the integer and the fractional quantum Hall effect. For the spin Hall effect, now we have predicted and observed a quantum spin Hall effect of the 2D topological insulator in 2006 and 2007. The question is, how do we make some quantum anomalous Hall effect? So to remind you, this will be just like a quantum Hall effect, but without any external magnetic field, but replacing them by magnetic moments. So we are again predicting that the topological insulators form a wonderful platform to realize this state of quantum anomalous Hall effect. And we basically propose that you take a topological insulator, and for this effect, it's a true 2D effect. So you're only talking about 2D topological insulators. And that if you have mercury telluride, you're putting manganese into the system, which is a magnetic element, and the coupling of the magnetic moment to the electronic structure in the system, we predict will give rise to quantum anomalous Hall effect. And in these newer topological insulators, we're putting chromium and iron into these topological insulators, and that's the prediction. So how does it work? So the basic picture in the case of mercury telluride is that basically you have this S band and P band, and they cross at one point. And so each one of these levels are doubly degenerate due to the time reversal symmetry. So at these crossing points, basically you have two levels, but four states are colliding with each other. And now when you go beyond to the non-trivial level, it's like the spin up components reach the quantum Hall effect of E squared over H, and the spin down components reach the quantum Hall effect of minus E squared over H. So altogether, on the non-trivial side, you still have no charge Hall effect because the sum is zero as dictated by the time reversal symmetry. But the difference is non-zero, and that's why it's called quantum spin Hall effect. But now, what happens if you break time reversal symmetry by these magnetic moments? So if you break the time reversal symmetry, the system will then, you have the spin up going now. In principle, these red and blue are no longer degenerate. So then you can have the spin up becomes non-trivial first before the spin down becomes non-trivial. So that tells you there must be some intermediate regime where the spin up is already displaying quantum Hall effect and spin down does not yet have a quantum Hall effect. So altogether in this regime, it will give you a charged quantum Hall effect, but now without any external magnetic fields or external orbital magnetic field, but purely due to the magnetic moments. And there are already some experimental indications, again from Würzburg, indicating, and they basically apply a tiny little field of 0.2 Tesla, and already the system going to a quantum Hall plateau regime. And what we believe is that the B field is not giving rise to any orbital quantization, but simply aligning the manganese moment in the system. So we're also predicting a lot of new material which can really realize the quantum anomalous Hall effect, but without putting randomness. So in this proposal, manganese going rather randomly into mercury telluride. The question is whether you can find a stoichiometric material, which is quantum anomalous Hall. So it's like a ferromagnetic insulator in the bulk, but has non-trivial edge states, which is chiral edge state. And we're very recently, if you follow us on the preprint archive, we're predicting that this material will realize the quantum anomalous Hall. So now let me move on to the subject of interacting topological insulator, which is kind of the frontier field now. But let me first tell you what is the most general definition of a topological insulator, let's say in the presence of interaction. Again, we use the tool of effective theory. So if I have a system, no matter how interacting it is, I can couple the system to some external electromagnetic field. I integrate out my fermions in the system, and then I will get the effective action. And for ordinary insulator, the effective action is nothing but the Maxwell action, with some coefficients such as epsilon and mu. And that tells you about the dielectrical constant and the magnetic permeability in the system. So what is also possible when you integrate out the electron is not only to get a term E squared minus B squared, which is the Maxwell action, but you can also get a term which is E dot B, which is also a possible quadratic term, but a mixing term between E and B. So now it turns out that this term is a topological term. How do we see that? We can see that very quickly. When you write E dot B in covariant notation in the covariant field tensor, then you basically have F times the dual field tensor, F dual, which is epsilon times F. So this term, actually, even in curved space, you can write it down without any metric, because the contraction is achieved using the epsilon case. So it's in this precise sense that this is a topological term. And then further evidence is that when you write F in terms of A, the F dual is actually the derivative of the transcendence term. So what appears like a bulk term here actually is a transcendence term on the surface. So now, because of this reason that it's topological, it turns out that the effective action or the partition function only depends on this parameter theta periodically. So theta going to theta plus 2 pi is a period of the system. So now what happens when you study that term under time reversal? Under time reversal, E goes to minus E, but B goes to minus B. So then that's like saying effectively theta goes to minus theta. But so that is why usually any finite value of theta naively seems to break time reversal symmetry. It goes to the opposite value. But there's only two special values. Obviously, when theta is equal to 0, it's time reversal invariant. But also for the special value when theta is equal to pi, then the time reversal of that is minus pi. But minus pi and pi differ from each other by 2 pi, which is the period of the effective partition function. So that's why it also preserves time reversal symmetry, but in a highly non-trivial way. So this is a general proposal of what is the general definition of a topological insulator is. And that is an insulator which is time reversal invariant, but in the theta equals to pi class. So first of all, this gives a general definition for interacting topological insulator, but also tells you what's physically to measure and what's exactly quantized in the case of a topological insulator. So these coefficients, when I changed my material slightly, they will generally change. But this theta coefficient cannot change. It can only take two discrete values, either 0 or pi. And that's why this is a topological response, which is strictly quantized. So you can study this response, and basically leads to the effect that you apply a magnetic field, you get a polarization, and you apply electric field, you get a magnetization. And the constant of proportionality is exactly quantized. The theta can only be 0 or 2 pi. So that term that you add to the standard Maxwell action can also change the Maxwell equation. This is now called the axion electrodynamics, which has been proposed in high energy physics also, but now finally we have a place in condensed matter physics to realize this. So this is basically the effective Maxwell action derived not only from the Maxwell action, but from the FF dual term. So now you may wonder whether there's kind of a expression for this theta angle in the condensed matter system. And we actually found a very nice and beautiful one. And this is actually, if you have a three-dimensional system, you will have three-dimensional momentum space integral, and it's nothing but the Chern-Simons term for the Barry phase curvature, anti-Barry phase gauge potential. So there's a very nice and beautiful expression for this theta term in terms of a Chern-Simons term in momentum space. So that's what we discovered in 2008. So now how do you turn this into a real experimentally observable effect? So we said that this system have a Dirac cone which is protected by time reversal symmetry. So anytime when we say it's protected by time reversal symmetry, it almost sounds like something bad happens when you put time reversal symmetry. Actually, when you put enough of time reversal symmetry breaking, even more interesting happens. That's if you put magnetic impurities on the surface of topological insulator, they basically tend to order ferromagnetically because the RKKY interaction is always ferromagnetic. When the Fermi level is at the Dirac point, there's no KF, there's no oscillations. It's always ferromagnetic, and it tends to align the moments so that a gap is opened up. And once such a gap is opened up, you basically have a ferromagnetic ordered moment on the surface. So in that case, an experiment also has been done at Stanford. They basically put iron or manganese into this topological insulator, and after you put enough of them, you actually see a surface gap that opens up. So now why is this good for? So if you have this surface magnetic moment, a uniform gap opens up, but then in the case when you have a magnetic domain wall, on that there will live a chiral mode which only propagates in one direction. And that is analog to the axion string which has been proposed in the literatures of energy physics. But again, we can realize these experimentally, and I believe we're very, very close to realizing them. But not only it's a fun kind of effect to observe experimentally, but this can actually be very useful because, again, these chiral modes propagate without any dissipation, no possibility of backscattering, and one can really do some, not only test some fundamental physics, but also build some wonderful new devices. So now we can also, yeah, maybe I skipped that. One issue we are discussing in the case of interacting topological insulators is that so far spin orbit coupling in the single particle level plays a very, very important role for giving rise to this topological behavior. The question is whether you can have a system which has no spin orbit coupling, but only interaction, whether that can give rise to a topological insulator. So we call such state topological Mott insulators. And we actually found the example of that. So if you have a two-dimensional honeycomb lattice with ordinary hopping, without any fancy hopping or spin orbit coupling, but with also conventional interaction term, for example, U term for on-site interaction, and V1 term for a nearest neighbor interaction, and V2 term for the next nearest neighbor interaction. And in the limit when V2 is large, which may or may not be physical depending on the system, we actually showed that in this case, without any spin orbit coupling to begin with, the system goes into a phase which is a 2D topological insulator. And then we're also talking about fractional possibility, just like for quantum Hall effect, you have a quantum fractional quantum Hall effect. Now for a topological insulator, you can also have a fractional topological insulator. And that's defined in the case that this theta angle, which previously can only take value between 0 and pi, but now can take some fractional angular value. And that is also something which is very interesting to look for. So maybe let me almost conclude my talk by showing this last slide, that you have now the concept of an insulator with a gap, and you have this gapless edge state, either in the case of quantum Hall effect, which is chiral, or the quantum spin Hall effect of 2D topological insulator, which is helical. They can go in both directions, but the direction is related to the spin, and this degeneracy cannot be removed. So now, a superconductor bears some superficial resemblance to an insulator in the sense they all have a gap. So now you can also have a superconductor which has a full gap, quasi-particle gap in the middle, in the bulk, but then you have gapless quasi-particle state on the boundary. So this is the notion of a topological superconductor. So, and this is, and the difference is here, the charge is conserved in the insulating case, and you have a complex chiral fermion here. But in a superconductor, the particle number is not strictly conserved. You only conserve modulo 2. So then the edge state is not only chiral, but chiral Majorana, a real fermion, which is not only going in one direction, but does not have a particle and antiparticle type. It only has one type. And for the case of quantum spin Hall effect, the analog will be a helical superconductor, and that has a fully gapped superconducting state, but then it has this helical Majorana fermion state. So these are the states we're still looking for in nature. Actually, there's one system for which we know for sure it is a topological superconductor, and that's the system of helium-3 B base. That it has a full pairing gap, P-wave pairing gap in the bulk, but has a gapless surface state, which is a Majorana cone rather than a Dirac cone. And the reason we believe that is because when you look at the effective BDG Hamiltonian or BCS Hamiltonian for helium-3, remarkably, it turns out that term by term, it's identical to the model I just discussed with you for the 3D topological insulator proposed by a group for bismuth selenide and bismuth telluride. So there you have an insulator and you have a Dirac fermion. But here the Hamiltonian is expressed in the non-Boole basis. So you have to remove half of the degree of freedom in the end. And if you have a Dirac cone on the surface for a topological insulator, then for a topological superconductor, when you remove half of the degree of freedom, it becomes a Majorana cone. And that's something we know for sure happens in helium-3. But conclusive experiment is yet to be done. So now let me conclude that this is a really exciting field. It's a very good field for theorists because we were able to predict a number of these materials and properties before the experiments were carried out. And so the materials can be predicted and designed. And the frontiers of the field now focuses on improved material properties, and that takes some patience. Even for something like silicon, it took a long time for the material property to improve. But in the meanwhile, we're looking for new topological insulators. We're looking for these beautiful axion effects associated with magnetic monopoles and also effects of Majorana fermions. We're trying to understand topological superconductors, quantum anomalous Hall effect, I believe we're very close, and then strongly coupled topological insulators. And here are some of the review articles you can look at. Thank you.
Thank you very much. So, questions? Understood everything? David?
A very naive and simple question. So you talked about this electromagnetic action.
Yeah.
And then the E squared plus V squared, and I recognize that as the energy density of
Yeah.
the electromagnetic field.
Yeah.
But you have this E dot B.
Yeah.
I guess I'm used to thinking that electric and magnetic fields are orthogonal, so that should be zero.
Yeah, but that's only if you assume that your basic equations are E squared and minus D squared.
Yeah.
If you actually have these, you actually have a mixing between E and B.
So what does that mean for, say, electromagnetic wave propagation through such an
Yeah, so you leads to this beautiful effect. One of the effects, which is maybe the easiest to explain, is that for ordinary insulator, if I put a charge, I will get an image charge. Here, if I put a charge, the image is a magnetic monopole. So this set of equation has been studied to great detail, and actually, this axion electrodynamics is proposed to. Some people believe that the polarization we observe from cosmic background radiation comes from. So it basically leads to the following effect: that if you have a linearly polarized light, if it goes through this axion media, it rotates this angle. And some people believe the polarization in the cosmic background radiation comes from this effect. Yeah.
You mentioned these new materials that have over 50 new
Heussler materials. Yeah.
Heussler materials.
Yeah.
Are these easy to produce?
Yeah, it depends how. Yeah, for series was quite easy for us to calculate, but because they're not binary materials, they're ternary materials, they're a little bit harder to process. But there are solar cell material which contains 4 elements and manufacturing grade. So I think with enough investment, they will all come out. Yeah.
Well, you were talking about topological superconductors. Should we have a spin-treated superconductor?
Yeah. Yeah.
So,
Yeah. So it's the case for helium-3 B phase. Yeah.
You mentioned the Mercury telluride as
Yeah.
clean topological insulator.
Yeah, yeah.
Does it still mean you have impurities?
Yes, there are always impurities, but we're already in a regime where these bulk effects are not ruining the 2D quantum core.
So in what sense is it clean?
In the sense that these plateaus are quantized without ruined by the impurity. So in bismuth selenide, no one has done such an experiment yet. If you take a thick layer of bismuth selenide, put that in a magnetic field, the Hawk constants is all over the place. The precise sense that this is clean is that these plateaus are quantized. So the impurities are not leading to bulk conductions and short-circuiting the surface through that. Yeah, you can never find a material which has no impurities, but the impurities are not contributing to the transport.
So let me ask a question also. Concerning this quantized anomalous
Yeah.
effect, is
Yeah.
there topological classification?
Yeah, it's the same as quantum Hall.
It's the same.
Yeah,
It
yeah,
doesn't
yeah,
add
yeah,
anything new
yeah,
to
yeah,
that.
yeah. The only thing new is that it does not have runout.
Okay, if there are no more questions, we thank Zhang.